Hi everyone, I'm Jack from Stanford. I will be introducing a new concept named pseudo-entanglement, which demonstrates subtle interplay between two important notions in quantum computing. One is pseudo-randomness, and the other is entanglement. It's a joint work with Aaronson, Adam Bouland, Bill Fefferman, Soumik Ghosh, Umesh Vazirani, and Chenyi Zhang. First, let's briefly review the randomness in classical computing. So randomness is a very useful resource for classical algorithms. It has many applications. For example, we want to do some hashing. And for hashings, we usually pick a random functions, h, that maps n bits to m bits. And usually m is much smaller than n. And so here we meet an issue is that we only have access to limited number of truly random bits. And here, in order to implement a truly random hash function, we need exponentially many random bits. It's so many random bits, and we usually do not have such result. To overcome this issue, people come up with a notion named pseudo-randomness. The idea is to use much less randomness to efficiently spoof truly random bits. For example, given a C string with polylog length, we want to expand this C string into an n-bit string in a way that it is indistinguishable from the truly random n-bit string. So here there's a word very important, which is indistinguishable. And for different applications, we have different notions for the indistinguishability. So if we want any k bits of our output strings to be info-theoretically indistinguishable from the truly random string, then we have a notion called KYC independent function. If we want the output string to be computationally indistinguishable from the truly random string, then we have the notion called the PRG, the pseudo-random generator. And the both notion, they use exponentially less randomness than the truly random function. So they have many applications in cryptography, algorithm design, analysis of data structure, and etc. Next, I'll talk about a notion named entanglement. And quantum entanglement is a fundamental resource for quantum computing. And entanglement is a necessary ingredient for quantum speedups. If there is no entanglement in a quantum algorithm, then this quantum algorithm can be efficiently simulated by a classical algorithm. And quantum entanglement is not exactly analogous to the role of randomness in classical computing. We can pull quantum entanglement out of quantum algorithms. The exact role of entanglement in the speedup of quantum algorithms is still mysterious. And there are many different measures of entanglement. For our paper, we mainly focus on the von Neumann entropy, which is defined as follows. The main question of our paper is it possible to spoof entanglement just like we can use pseudo-randomness to spoof the truly randomness? In this paper, we introduce the notion pseudo-entanglement. Our goal is to find two ensembles of efficiently constructible quantum states, and one ensemble of quantum state has high entanglement, and the other has low entanglement, but the two ensembles of quantum states are computationally indistinguishable. And we give the first construction of pseudo-entangled state with exponential reduction in entanglement, which means the Schmidt rank and von Neumann entropy of two ensemble of quantum states have an exponential gap. Our construction is fairly simple. We first pick a pseudo-random subset S in 2 to n and construct a subset state which is a uniform superposition over S. Finally, we apply a pseudo-random binary faces to the state. And by changing the size of S, we can change the entanglement. Moreover, these states are pseudo-random states, which means they are computationally indistinguishable from the uniform random states, aka higher random state. And our construction has many applications, ranging from new property testing bounds, entanglement distillation, and connections to quantum gravity. Now let me introduce some background of the quantum pseudo-randomness. The goal of quantum pseudo-randomness is to spoof the Haar measure on the states or unitaries. I have mentioned that the Haar measure, you can think of it as a uniform distribution over all quantum states or quantum unitaries. And so the motivation is that in many quantum algorithms, we will use the hard random states and hard random unitaries, like in the randomized benchmarking or in the shadow tomography. So the issue is that you cannot efficiently generate the hard random states or hard random unitaries. The solution is that we try to find efficient ways to spoof the Haar measure. So formally, we want to find the pseudo-random states or pseudo-random unitaries, which have short quantum circuits. So they're efficiently constructible, but they are indistinguishable from the Haar random states in certain sense. The usual approach to spoof the Haar measure in the literature of quantum information is a T design, which is infotheoretically indistinguishable from the Haar measure. Formally, a quantum T design is an ensemble of quantum states with the property that no algorithm can distinguish T copies from the truly random states. It has many important applications like the randomized benchmarking, efficient shadow tomography, and connections to quantum gravity. And there exist many efficient constructions of T designs. As opposed to the literature of quantum information, in computer science, we generally talk about a different notion of computational pseudo-randomness, which is these computationally pseudo-random states are efficiently preparable quantum states that they are not distinguishable from truly hard random states by any efficient quantum algorithm given polynomially many copies. And this notion is firstly proposed by Liu Song in 2018. This notion often requires mild cryptographic assumptions, like the existence of quantum secure one-way functions. Now, let's briefly compare the two notions. The one is T-design and the other is computationally pseudo-random states. And for T-design, no algorithm can distinguish them from the truly random states because it's an infotheoretic notion. However, the number of copies is fixed by is a fixed polynomial t. And as for the computationally pseudo-random states, there's some algorithm, but all efficient algorithms cannot distinguish them from the hard random states. However, it can take an arbitrary polynomial in many copies to keep the PRS to be secure. What is the relation between pseudo-randomness and quantum entanglement? A typical hard random quantum state is maximally entangled, which means if we cut n qubits into 2 halves, then the entanglement of this bipartition is n over 2 minus O of 1. And the quantum T design are also close to maximally entangled for any T is greater or equal to 2. The entanglement of T design is also n over 2 minus a constant. As for the computationally pseudo-random states, and JLS, in their paper, they give a lower bound, which implies that any pseudo-random state must have little omega of log n entanglement across most cuts. So you can see that there is a huge gap between the upper bound, which is n over 2, and the lower bound between little omega of log n. So our question is it possible that the computationally pseudo-random states can have a very low entropy as low as a little omega of log n? And we give a positive results in our paper, which is the computationally pseudo-random states do not need to be extremely entangled, and they can actually saturate this little omega of log n lower bound. Our main result is that for any function f of n, which is between the little omega of n log n and the big O of n, there is an ensemble of pseudo-random states where the entanglement entropy across almost all cuts are theta of Fn simultaneously, which is exponentially less entanglement than needed for infotheoretic security. And our construction relies only on a standard cryptographic assumption, which is the existence of quantum secure one-way function. Next, I will give you a proof sketch of our construction. Now, let's first recall our construction. Our construction is a subset phase state. To construct this state, we first pick a pseudo-random subset S, and then we reconstruct a state, which is a uniform superposition over the subset S. And finally, we apply a binary phases to this state. Note that the Schmidt rank across any cut of this state is at most the size of S. So the von Neumann entropy is at most log of size of X. So we can control the size of S to control the upper bound of von Neumann entropy. Our subset phase state is very easy to construct. To construct this state, we assume the size of the subset S is 2 to the f of n. To prepare our state, we first prepare the uniform superposition over strings which the last n minus f of n bits are 0. And then we apply a pseudo-random permutation pi to obtain a uniform superposition over a random subset. Finally, we apply a pseudo-random function f to obtain the phases of the final state. You can see that there are two pseudo-random functions we use to construct this PRS. The one is the pseudo-random permutation pi in the second step. The other is the pseudo-random binary phases in the third step, and both ingredients can be implemented by quantum secure one-way functions. The next question is, why are these subset phase states indistinguishable from hard random states? We will first show that if phases and subsets were chosen randomly, truly randomly, then these states would be statistically close to hard random states. Next, by replacing these truly random faces and truly random subsets with pseudo-random faces and pseudo-random subsets. And we can show that these two ensembles are computationally indistinguishable. The first step is to show that the truly random subset phase states are close to hard random states. By a well-known result, the density matrix of unknown hard random states are projectors onto the symmetric subspace, which is as follows. Next, the random phase states are very close to the projectors onto a symmetric subspace. This result has been established in the literature. And this is also true for subset states. So subset phase states are close to the projector onto a symmetric subspace of states with spaces support in S. Now the problem boils down to how the following two states are related. The hour states, the density matrix is the average over the projectors onto symmetric subspace of the subset S, where S is a random subset with a fixed size of f of n, and the other is the hard random state, whose density matrix is a projector onto a symmetric subspace over the size n. We show that these two states are very close in trace distance, and our proof uses type enumeration methods. As a corollary, that the pseudo-random subset phase states are PRS. The proof is by a standard hybrid argument. The first step is that the hard random state is info-theoretically close to the truly random subset phase state, and the truly random subset state is computationally indistinguishable from the pseudo-random subset phase state. Finally, let me briefly talk about some applications of pseudo-entanglement. The first application is a new lower bound on MPS testing, or matrix product state testing. The problem is that given some copies of an unknown state, you want to test whether it has a k-bound dimension MPS description, or if it is far away from any MPS. And our results gives a new lower bound on this problem. The second application is a new lower bound on the estimation of the Schmidt rank. And we also give a new lower bound on this estimation problem. Finally, the third application is a connection to the complexity of ADS-CFT. The ADS-CFT is a scheme in theoretic physics which conjecture there's a duality between the quantum gravity and the quantum mechanical system. So the major theme is that the entanglement structure in the CFT is equivalent to the geometry in the bulk state. And our results implies that entanglement is a quantity that cannot be efficiently observed. As a corollary, if the corresponding geometry in the bulk is feelable or efficiently observable, then the ADS-CFT dictionary must be hard to compute. As a summary, in this paper we propose a new notion, pseudo-entanglement, which is quantum ensemble of quantum states that can computationally spoof high-entangled quantum states with exponentially less entanglement across all cuts. We left some open problems. The first one is, are there other constructions of PRS or PES? The second one is, are there more applications to the physics, like learning the phases of matters, like PRS state with CFT-like entanglement structures? or create new crypto primitives from the pseudoentanglement? Or are there any more Nisky-like implementations of pseudo-randomness? Thanks for listening.